So, Max, I was trying to explain to my mom what I do for a living, and she asked if I'm basically just teaching computers to remember stuff better,
Well, in a way, she's not wrong, especially when we look at these RAG systems we've been talking about lately.
right? And I was like, Mom, it's not just about remembering, it's about how they connect the dots between what they remember, which, coincidentally, is exactly what today's paper is all about.
Perfect segue, Casey. Welcome, everyone, to another episode of Totally Unprofessional Peer Review. I'm Max Stone, your resident theory nerd who's obsessed with metrics and methodology.
And I'm Casey Park, developer extraordinaire with an eye for structure and flow. We're excited to have you join us for another deep dive into the cutting edge of AI research.
Today, we're looking at a fascinating paper titled Improving Multi-Step RAG with Hypergraph-Based Memory for Long-Context Complex Relational Modeling. Quite a mouthful, isn't it?
It really is. But strip away the academic jargon, and what these researchers are doing is pretty revolutionary. They're basically saying, hey, what if AI memory worked more like human memory, connecting related concepts instead of just storing isolated facts?
Exactly. Traditional RAG systems have been using memory as essentially a glorified notepad, jotting down facts but not really understanding how they relate to each other.
Which is why this HGME approach is so interesting. They're using hypergraphs to create these complex webs of interconnected information, allowing the AI to actually reason through problems rather than just regurgitate facts.
And the results are impressive. We're talking about significant improvements in global sense-making capabilities across multiple tasks. It's like the difference between having a filing cabinet versus having an actual thinking assistant.
Ah, you know what this reminds me of? Remember that time I tried to solve that murder mystery game by just collecting all the clues but not connecting them?
Oh my god, yes! You had that elaborate spreadsheet with every single clue meticulously documented.
But I couldn't solve it because I wasn't seeing the relationships between them. Traditional RAG systems are basically me playing that murder mystery, great at collecting information, terrible at putting it together.
And HGME is like having Sherlock Holmes in your corner, drawing those red strings between all the evidence on the conspiracy board. So, are you ready to dive into how these hypergraphs are revolutionizing the way AI systems think?
Absolutely! Let's start by breaking down the limitations of traditional memory designs in multi-step RAG systems, and then see how HGME transforms the game.
So, let's break down what the paper means by limitations of traditional memory designs. In multi-step RAG systems, memory has traditionally been implemented in some pretty basic ways.
Right, and from what I'm reading here, the most straightforward implementation is basically just having an LLM summarize the interaction history into plain text. It's like keeping notes during a conversation.
Exactly. The paper mentions this has been widely adopted since early studies by researchers like Lee and Trivedi, and even in commercial systems. But there's a fundamental problem with this approach.
Let me guess. These unstructured memory mechanisms can't be manipulated effectively. They're just static text.
Bingo! The paper describes existing memory designs as passive storage that accumulates isolated facts. They're essentially just collecting information without understanding the relationships between those facts.
It's like having a bunch of puzzle pieces but no idea how they fit together. I've worked with systems like this, and they're great at retrieving information, but terrible at making connections between different pieces of knowledge.
The paper specifically calls out that this static nature overlooks the crucial high-order correlations among primitive facts. In human terms, that means these systems miss the forest for the trees.
I'm seeing that there have been some attempts to improve this, though. The paper mentions React, which incorporated reflections to integrate available information for subsequent decisions. That's at least a step toward a more dynamic memory system, right?
Yes, but still quite limited. React and similar approaches represent what the paper calls a simple form of memory. There have been other studies that save agent behavior, like task decomposing, execution tracking, and result verification to manage task context more effectively.
And then we have chain of thought and multi-round RAG approaches, where working memory is represented as iteratively updated records of reasoning steps or retrieved evidence. It's getting better, but still not quite there.
The evolution is interesting, actually. Some researchers have tried to take it a step further by adopting graph-structured working memory. The paper mentions work by Liu and Li that enhanced multi-step RAG this way.
Oh, like no trace. The paper specifically mentions that system using a graph based working memory to trace relevant knowledge through multi step RAG execution. But even that has limitations, right?
Exactly. The paper points out that these graph-enhanced approaches do not effectively support modeling high-order correlations among multiple entities/relationships because each edge in their graphs can only describe binary relationships, basically just connections between two things.
Which is a problem because real world knowledge is rarely that simple. Things are connected in complex, multidimensional ways that binary relationships just can't capture.
Precisely. And there's another fundamental issue. These structured indexes or memories are typically constructed during an offline indexing stage before actually responding to user queries. They're static, not dynamic.
So they can't evolve or adapt as the conversation or reasoning process unfolds. That's a huge limitation when you're trying to solve complex problems that require building understanding over multiple steps.
The paper even provides some experimental evidence of these limitations. It compares various baseline methods, including DeepRAG and ComoRAG, which are equipped with working memory, and finds some interesting patterns.
I see that. Different systems have different strengths based on their representation methods. HippoReg V2 uses knowledge triples, which are great for representing facts but limited for covering events and plots. So it performs well on some tasks but falls behind on others like narrative QA.
Meanwhile, GraphRag and LightRag are better at building global representations, but struggle with fine-grained details. They excel at tasks like Prelude and narrative QA, but have their own weaknesses.
And here's the kicker. The paper explicitly states that multi-step RAG methods that mainly use working memory to iteratively generate subqueries struggle with sense-making questions, where integrating higher-order relationships is essential.
That's the core limitation right there. Traditional memory designs in RAG systems result in fragmented reasoning and weak global sense-making capacity in extended contexts. They just can't connect the dots effectively.
It reminds me of trying to understand a complex novel by just memorizing individual sentences. Without understanding the plot, you might remember a lot of details, but you completely miss the story.
That's a perfect analogy. And that's exactly why this HGMA approach with hypergraphs is so interesting. It's designed to overcome these limitations by creating a memory structure that can represent those complex, multi-dimensional relationships.
Exactly. So now that we understand the problem with traditional memory designs in RAG systems, let's dive into how HGMN transforms static storage into dynamic reasoning structures.
So now we get to the exciting part, HGM or the hypergraph-based memory mechanism. According to the paper, this approach extends the concept of memory beyond simple storage into a dynamic, expressive structure for complex reasoning and global understanding.
I love how they're completely reimagining what memory can be in these systems. It's not just a place to store facts anymore, it's an active reasoning component.
Exactly. Let's look at how they've structured this memory. In HGMM, memory is represented as a hypergraph. Now, unlike regular graphs where edges connect exactly two nodes, in a hypergraph, a single hyperedge can connect multiple nodes at once.
That's the key innovation here. The paper specifically mentions that a hyperedge can connect an arbitrary number, two or more, of vertices. This is what allows them to model those complex, multidimensional relationships we were talking about earlier.
Let's take a look at Figure 1 from the paper, which illustrates how this system works. It's quite illuminating.
Oh, this is helpful. So on the left side, we can see the RAG system at its TS interaction step. The LLM generates subqueries, retrieves information, and then evolves the current memory MT into MT plus 1.
And on the right side, we can see the memory evolving through three specific operations: update, insertion, and merging. Those colored circles represent different entities or concepts, and the boxes or hyperedges are connecting multiple entities together into meaningful units.
So each of those boxes is essentially a memory point in their system. The paper says the hyperedges can be treated as separate memory points, each of which corresponds to a certain aspect of the entire information stored in current memory.
That's right. And what makes this approach so powerful is how these memory points evolve over time. Let's break down those three operations they mention.
First, we have the update operation, which I'm guessing modifies existing memory points with new information.
Exactly. When new information is retrieved that's relevant to an existing memory point, the system updates that memory point to incorporate the new details.
Then there's insertion, which must be for when entirely new information comes in that doesn't relate to existing memory points.
Right again. The system creates new memory points when it encounters information that doesn't fit into the existing structure.
But the real magic seems to be in the merging operation. The paper says this builds higher order correlations among multiple existing memory points, facilitating the resolution of queries that require complex relational modeling with disparate facts.
That's where the hypergraph structure really shines. Traditional graph-based memories can only represent binary relationships, connections between two things. But HGME can merge multiple memory points together, creating these rich, multi-dimensional relationships.
Let's look at Figure 2, which shows an example of this memory evolving process in action.
This is fascinating. We can see how the memory evolves through these operations. Initially, there are separate memory points about different entities like Cuculia moth and Bombylius. Then, through update and insertion operations, new information is added.
And then the magic happens with merging. The system combines these separate memory points into a new, more complex memory point that captures the relationships between all these entities. It's connecting the dots between moths, Bombylius flies, and Anthophora bees in the pollination process.
Exactly. And this is crucial for complex reasoning tasks. The paper explicitly states that besides continuously accumulating primitive facts during the LLM's interactions with external data sources, the memory also gradually evolves into more sophisticated forms, capturing higher-order correlations for complex relational modeling.
I'm also noticing that the system has an adaptive retrieval strategy. It says it can perform either local investigation or global exploration depending on what's needed.
Good catch! This is another key aspect of HGME. The system can adaptively decide whether to dig deeper into specific areas, local investigation, or explore broader connections, global exploration, based on the current state of the memory and the query at hand.
And when it's time to generate a response, the LLM uses both the descriptions of all memory points and the text chunks associated with all the entities in the current memory, so it has access to both the structured relationships and the original context.
That's right. And let's look at how this memory evolving process affects performance over time. The paper includes some fascinating charts showing accuracy across multiple interaction steps.
These charts are telling. HGME consistently outperforms the baseline methods across different tasks. And look at that spike in performance around step 3 that suggests the memory is becoming increasingly effective as it evolves.
The paper also did an ablation study to determine which operations were most important. They found that removing any operation led to a performance drop, but removing the merging operation caused a substantially larger degradation than removing updates.
That makes sense. The merging operation is what builds those high-order correlations that are so crucial for complex reasoning. Without it, you're back to isolated facts without the connections between them.
It's like trying to solve a mystery with all the clues but no way to connect them. You're just staring at a pile of evidence without seeing the pattern.
Exactly. And what's really impressive is how this approach scales with complexity. The more complex the reasoning task, the more beneficial these high-order correlations become.
To summarize, HGME transforms static storage into dynamic reasoning structures through its hypergraph-based memory that evolves over time via update, insertion, and merging operations. This allows it to capture complex, multidimensional relationships that traditional memory designs simply can't represent.
And the result is a system that can actually reason through problems rather than just regurgitate facts. It's providing strong compositional representations that span from facts to plots, as the paper puts it, which enables the LLM to perform much better on tasks requiring global understanding and complex reasoning.
It's a significant step forward in making AI systems that can truly understand and reason about complex information. Now, let's look at how this theoretical advantage translates into practical performance improvements in the experimental results.
Now let's dive into the experimental results. The researchers really put HGME through its paces with some challenging datasets specifically designed for global sense-making tasks.
That's right. They focused on two main types of tasks: generative sense-making question answering and long narrative understanding. These aren't your typical QA tasks. They specifically required high-level understanding and global reasoning over evidence scattered throughout long documents.
I noticed they used documents with more than 100,000 tokens from Longbench v2, which is a lot of text to process, and they had GPT-4o generate queries that really test global understanding rather than just fact retrieval.
Exactly. They wanted to ensure the questions couldn't be answered by just looking at a specific sentence or paragraph. The system needed to integrate information from across the entire document to form a coherent understanding.
And they were careful about making the comparisons fair, too. All the baseline systems they compared against retrieved a similar number of passages, whether they were single step or multi step RAG methods.
Let's take a look at Table 1 from the paper, which shows the overall experimental results across four benchmarks: long bench comprehensiveness, long bench diversity, narrative QA, and prelude.
Wow, the results are pretty striking. HEME consistently outperforms all the other methods across every single dataset. For example, on long bench comprehensiveness, HEME scored 65.73%, while the best traditional RAG method only reached 61.62%.
And it's not just beating traditional RAG systems, it's also outperforming other multi-step RAG methods that do have working memory, like Deep RAG and Como RAG. The pattern is consistent across all the benchmarks.
I'm particularly impressed by the results with Quen 2.532b instruct in the bottom half of the table. HEME with this smaller model is matching or even beating some baselines that are powered by GPT-4o, which is a much larger and more powerful model.
That's a really important point. It shows that HEME's approach to memory management is so effective that it can help a smaller, more resource-efficient model compete with much larger models. That has huge implications for practical applications where computational resources might be limited.
The researchers also analyzed how performance changes across multiple interaction steps. Let's look at those charts.
These charts are fascinating. They show accuracy on three datasets: narrative QA, NOCHA, and prelude, across multiple steps of interaction. The blue line is HGME, while the orange and green lines are baseline methods.
What jumps out at me is that big spike at step 3 for HGME across all three datasets. On narrative QA, it jumps from around 38% at step 2 to over 50% at step 3. That's a huge improvement in just one step.
The paper specifically mentions that HGME achieves its best performance at step 3, consistently outperforming the baseline methods. This suggests that the hypergraph memory really starts to show its value after it's had a few steps to build those complex relationships we talked about earlier.
It's like watching someone solve a puzzle. In the first couple of steps, they're just gathering pieces, but by step 3, they've started to see the bigger picture and how everything fits together.
That's a great analogy. And what's interesting is that performance does dip a bit after step 3 in some cases, which suggests there might be a sweet spot for the number of interaction steps.
The researchers also did some ablation studies to understand which components of HGME were most important. Let's look at Table 2, which shows what happens when you remove different parts of the system.
This is where it gets really interesting. They tested two main aspects, the retrieval strategy and the memory evolution operations we discussed earlier.
For the retrieval strategy, they compared their adaptive approach that combines local investigation, LI, and global exploration, GE, against versions that only used one or the other. The results show that using either strategy alone leads to significantly worse performance.
Right, and for memory evolution, they tested what happens when you remove either the update operation or the merging operation. Both led to performance drops, but removing merging had a much bigger negative impact.
That makes sense given what we discussed earlier about the importance of merging for building those higher order correlations. Without merging, you're back to isolated facts without the connections between them.
The researchers went even deeper in their analysis. They looked at the average number of entities per hyperedge in the final memory for different types of queries. Let's check out Table 3.
Oh, this is interesting. They divided queries into two types: primitive queries that just ask for specific facts, and sense making queries that require complex reasoning and global understanding.
And what they found is really telling. For primitive queries, the full HGEM and the version without merging performed similarly, but for sense-making queries, the full HGEM significantly outperformed the version without merging.
And look at the AGFGEMNA column. That's the average number of entities per hyperedge. For sense-making queries, the full HGEMA has much larger hyperedges than the version without merging. On narrative QA, it's 7.07 entities per hyperedge versus just 4.10 without merging.
That's a crucial finding. It shows that HGEM is building these complex multi-entity relationships specifically when they're needed for answering complex questions. The system is adaptively forming higher-order correlations to enhance comprehension for difficult queries.
And notice that across all datasets, the average number of entities per hyperedge is consistently higher for sense-making queries than for primitive queries. This suggests the system is naturally building more complex relationships when the task requires deeper understanding.
Exactly. The paper explicitly states that these results indicate HGEM improves contextual understanding by constructing high-order correlations for complex relational reasoning, rather than relying on shallow accumulation of surface facts.
So, to sum up the experimental results, HGEMN consistently outperformed both traditional and multi-step RAG baselines across all datasets, with particularly strong performance on complex sense-making tasks that require global understanding.
And the ablation studies confirmed that its success comes from the combination of adaptive retrieval strategies and, most importantly, the ability to merge memory points to form those higher-order correlations that capture complex relationships between entities.
It's impressive how much of an improvement they achieved, and the fact that HGEMN with a smaller model could compete with baselines using much larger models suggests this approach could be really valuable in resource-constrained environments.
Absolutely. These results make a compelling case that hypergraph-based memory is a significant step forward for RAG systems, especially for tasks that require deep understanding and complex reasoning across long contexts.
After seeing these results, I'm starting to think I should implement a hypergraph-based memory system for my personal notes. Maybe then I'd finally remember where I put my keys every morning.
I'm not sure even the most advanced AI memory system could solve that particular problem, Casey. but I'd definitely be interested in seeing what other real-world applications could benefit from this approach.
Well, I think that about wraps up our deep dive into HGME today. It's fascinating how a simple shift from traditional memory structures to hypergraphs could have such profound implications for AI reasoning.
Absolutely. What I find most compelling is how this approach mirrors human cognition in many ways. We don't just store isolated facts, we naturally build connections between related concepts to form a coherent understanding of the world.
That's exactly it, and I'm excited to see how these hypergraph based memory systems might evolve in the future. Could we see them implemented in consumer facing AI assistants, or maybe specialized research tools?
I think both are likely. Any application that requires complex reasoning across large amounts of information could benefit from this approach. Legal research, scientific literature review, even education, the possibilities are vast.
Well, that's all the time we have for today's episode of Totally Unprofessional Peer Review. Thanks for joining us on this journey through the cutting edge of AI memory systems.
And remember, if you enjoyed today's episode, please like, subscribe, and leave a review. Your support helps us continue bringing these complex research topics to a wider audience.
And if anyone out there is working on applying hypergraph memory to help find lost keys, please contact me immediately. My morning routine desperately needs an upgrade.
Until next time, this is Max Stone.
And Casey Park, reminding you that when it comes to AI memory, it's not just about connecting the dots, it's about realizing the dots were actually a hypergraph all along.